So I promised you a last video where I would explain the workings of the frequency response calculation. And here we are. So I said you should expect this to be more mathy. I'd say this is first year engineering mathematics, or maybe even parts of a second year curriculum. But I'll try to be pedagogical about it. I'll start by actually just throwing the formula out there. Then we will rewrite it, break it down, and see if we can create intuition by analyzing the different parts and how the formula actually works to produce the frequency response of a filter. Hope you find this interesting. Let me start by introducing the two stars of this video. First, Leonhard Euler, very famous Swiss mathematician. And he was a very prolific mathematician. And one of the many very interesting formulas he produced is this one, very famously relating the exponential of a complex value to the difference between the cosine and the sine of the theta. So the exponential of minus, so j is the imaginary unit, theta is cosine theta minus the imaginary unit times sine of theta. And we'll see how this formula in just a moment makes it possible for us to rewrite the formula we need in a more manageable way. The second person I should remind you of is this gentleman, Jean-Baptiste Joseph Fourier, a French mathematician. And he is actually the inventor of the transform that is today called the Fourier transform. Equally extremely important in modern mathematics. So I always made it a point in my lectures to introduce sort of sources like this. And I think it's important to keep in mind the enormous contribution that these people had to mathematics. Anyhow, let me throw the formula out there. It looks like this. This is the formula for calculating the frequency response of a filter. So let me just get the nomenclature straight. So this, the capital H is the frequency response that you calculate at specified frequencies. So F, remember we are in 2D, so we need two frequencies. Frequency along the x and the y-axis. So this could, for instance, in terms of relative frequency, be 0.1, and this could be 0.2, for instance. And that would produce one value of the frequency response for horizontal frequency 0.1, vertical frequency 0.2. To calculate that, you sum over the rows and the columns of the filter. So here I'm assuming we're looking at a 3x3 filter, so we index the rows -1 to 1. So the center pixel in the filter will be indexed 0, 0. Likewise, the columns, they go from -1 to 1. Then we pick out the values of the filter kernel and multiply each one of them by this expression here. So the exponential of, again, minus the imaginary unit times 2 pi, and then in the parentheses the x frequency times the m index and the y frequency times the n index. And so this is all in a way, but it doesn't really create, at least in my mind, much intuition into what is actually going on. So what I suggest is that we apply Euler's formula to rewrite this in a slightly different way. So the only thing I'm doing here is I'm replacing this complex exponential with its expansion in terms of cosine and sine. So you recognize this argument 2 pi, etc., that you find here. It's in the exact same form in this formula. And that allows us to break this down into two parts, one for the real part of the frequency response and one for the imaginary part. So you see that the real part of the frequency response, well, again, the sum over the rows and columns of the filter times these values that you generate by taking the cosine of 2 pi times, and then the frequency in the x direction that we consider times the m index, plus the frequency in the y direction times the n index. Likewise for the imaginary part, just we're using sinus, and remember we need to negate it since it's negative here. But looking at it this way, it's hard to sort of see what is actually going on. So I'm going to switch now to explain this in a graphical sense that I think will make it easier to grasp what is actually going on here. Now here I'm just showing you how the real part of the frequency response is calculated. So remember the filter coefficients and multiplied by the cosine terms. And basically we're just taking element-wise products of the filter values with the pre-calculated cosine terms. And to begin with, I'm collecting all these products in a matrix with the final product results. And as we finish calculating these products, we basically will just sum all the values in the product matrix. I'm showing you here. We take that matrix, we sum the values, and that produces the real part of the frequency response, so just above 0.75. And if you remember from high school mathematics, what we did here is basically an inner product, right, of the filter coefficients with the pre-calculated cosine terms. And the inner product is the same as the projection of one matrix or vector onto another. And the inner product will be large if the vectors point in the same direction in space, meaning that they basically are similar. So what we're doing here is basically projecting our filter values or filter coefficient values onto a set of values that we compare the filter values with. And the whole clue to understanding what the calculation of the frequency response amounts to is understanding what are actually these sets of coefficients that we are projecting our filter coefficients onto, and or comparing them with, if you like. And that is much clearer if, instead of considering a 3x3 filter, which basically is projected onto a 3x3 set of cosine values, which sort of makes it hard to visually see what are we projecting onto. If we switch to a much larger filter, like a 32x32 filter, meaning that there will be 1024 values, so each filter coefficient will then be 1 over 1024, and then it's much easier to see the shape or the visual appearance of what we are projecting onto. In this animation, I'm calculating the frequency response in exactly the same way, but for a larger filter, as I said, a 32x32 averaging filter. So each filter value now has a value of 1 over 1024. And I'm considering the frequency response at x and y frequency or relative frequency of 0.01 and 0.02 cycles per pixel. So a slowly varying variation. And now you see what it is we're actually projecting our filter onto. We're basically projecting or comparing it to a slowly varying sinusoidal or co-sinusoidal field and asking, are the filter coefficients similar, or would the image of the filter coefficients be similar to what we're seeing in the cosine basis? And if you look at the final result, 0.38 roughly, it shouldn't come as a surprise that we have there is some similarity here, right? The similarity isn't zero. That's because a large part, the central part, the part that is blue in the illustration, has rather high values, and they are dominant, right? There are more of those than the negative values. So when you multiply a constant image with this cosine image, first of all, you see you get the same result, and that shouldn't come as a surprise. The filter coefficients are all equal, so we're basically reproducing the values of the cosine basis. And when we sum that, we get a positive sum because all constant image actually is somewhat similar, right, to this slowly varying cosinusoidal field. And notice that since the positive values are in a majority, we end up actually getting a positive result. Now, in this sequence, I'm showing you the exact same thing, but for a higher frequency. And now notice that I'm comparing my image, or the image consisting of the filter coefficients, onto a much more rapidly varying cosinusoidal field. And well, as I showed you in the last sequence, the result has exactly the same shape. But now notice that since you're summing over roughly the same amount of positive and as negative values, you get a result close to zero. And that shouldn't come as a surprise, because now you're comparing a constant image, so the image corresponding to the filter coefficients, with a very rapidly varying field, and then there is no similarity, or little similarity anymore, right? So this is basically what you're doing when you're establishing the frequency response, or in this case, the real part of the frequency response. You're just asking yourself, how similar is my set of filters to varying types of these cosinusoidal fields? And in the case of a constant filter like this one, so an averaging filter, the projection or the similarity will be high when the frequencies are very low, because then you get low, slowly varying images that you compare with. As you increase the frequency, as in this case 0.1, 0.1, you're comparing to something that actually varies rapidly, and there is no similarity anymore. So the system is telling you that in this case, the filter no longer, or the image of the filter coefficients no longer really resembles the basis you're comparing it to, responds with a very low value for the frequency response in this case. So there is one thing remaining to be done here, and that is to consider, what about the imaginary part? Remember, we split the frequency response into a real and imaginary part. And so far, we've just looked at how the real part is calculated. And to illustrate the importance of the imaginary part, let's consider not the averaging filter, but, as you're seeing in this animation, the Sobel X-kernel. And again, we're considering this for a frequency of 0.1, 0.1, so a relatively rapidly varying sinusoidal field. And notice that the Sobel X-kernel is anti-symmetric about the vertical direction. And the cosine image I'm projecting this onto, or making the inner product with, if you like, is symmetric about one direction in space, or in 2D space, meaning that when you project something anti-symmetric onto this, then the projection will be zero, or very close to zero, as you see we're getting in this case, right? And this is where the imaginary part comes into play, because the imaginary part, as you remember, uses sinus. And if you remember from, I think this is high school mathematics, the sinus function lags 90 degrees behind the cosine function. So in this case, the sine basis images are going to be anti-symmetric along the same spatial direction as the cosine was symmetric about. So now we're projecting something antisymmetric onto something antisymmetric. And you'll notice that in this case, we are getting a rather important response, which makes sense. I mean, if you do apply the Sobel X to an image like this with a clear negative to positive gradient going from upper left corner to lower right corner, then you do expect a significant response, right? So this is where the imaginary part comes into play. Basically, you're doing an analysis of your filter, not only comparing it to a cosinusoidal type of basis image, but also the same images but phase shifted by 90 degrees, so the sinus version of them. That makes it possible to catch also the effect that antisymmetric filters have in terms of frequency response. Now, this is also why a filter, for instance, like the Sobel filter or other gradient filters, are often referred to as quadrature filters, because their frequency response is basically determined by the imaginary part of the frequency response, which actually lags 90 degrees behind the real part. And that's often referred to as a quadrature response, if you ever encounter that term. There is one thing I have shoved under the carpet to a certain extent. You remember I told you that the frequency response H can be split in a real and an imaginary part. So the real part corresponding to the cosine terms, the imaginary part to the sine terms. And you remember from high school algebra, if you call the real part H and the imaginary part B, then the frequency response can be written as A plus JB, J being the imaginary unit. And in that case, it's easy to see that the magnitude of the frequency response becomes the length, if you like, or the A squared plus B squared, and you sum those and calculate the square root of that. And that gives you basically the length or the magnitude of the frequency response. And for most practical purposes in image processing, that's what we're interested in. But you can also use the phase angle of the frequency response to consider something called the phase response of the filter. My experience in image processing is that it's something you relatively rarely see. You did see it a little bit earlier in this video when I told you about the term quadrature filters, so typically reserved for derivative or edge detection filters. As you remember, they will typically project much more stronger onto the sinus part than the cosinus part, and since the sine lags by 90 degrees the cosine, these filters are often called quadrature or 90-degree filters. That's, in my opinion, about as close as you ever get to hearing about the phase part of the frequency response. But do be aware of the fact that you can calculate the phase response, and for certain cases it can certainly be useful. I'll stop my discussion of frequency responses for now. I hope you learned something from this. At least a takeaway, I think, should be that you can read the frequency response as a projection of your filter kernel onto a whole series of sinusoidals at varying frequencies. And if your projection onto a specific sinusoidal is large, then that means that your filter kernel basically resembles that sinusoidal. That's how you can interpret what the frequency response actually does. In my next series of videos, I'll focus on something completely different and less theoretical. We'll look at optical character recognition, so reading basically text, in heritage documents in particular, we'll look at how to read Gothic text, so text printed with Gothic fonts. And this is a field where classical image processing is very useful because you can use it to generate synthetic data for training networks to better read these very particular fonts. Hope to see you there and hope you enjoyed this video, and let's do some optical character recognition.